Right, welcome back. In today's lesson, we're going to go through some questions on energy and forces. Alright, so I'll skim through those that the child got it correct. So this child placed 3 iron rings over a wooden rod and observed the following situation. And you notice that A is floating above B. So what causes it to stay afloat? There must be some force of repulsion, a force that is a non-contact force that acts at a distance. You know there are 2 kinds of forces. One is gravitational force, but that pulls things down. So this one that can repel and push things away will be your magnetic force of repulsion. So be careful, the word repulsion is here. Number 4 is correct. The table shows the amount of force needed to pull an empty box over 4 different surfaces. Now, we are dragging over different surfaces, therefore you're talking about frictional force. And if there's more frictional force between 2 surfaces, that will require more force to overcome the friction. If this is a surface and this is a box that you are pulling it across, frictional force is a force that opposes the direction of motion. So this is your frictional force. Okay, your frictional force opposes direction of motion. And if the floor is very smooth, you'll use very little force to pull it. If the floor is very rough, there's increase in the amount of friction between the bottom of the box and the surface. There will be more frictional force overcome, so you will need to use more force to pull it. So which is the smoother surface? You look for the force that the lowest, and that'll be B. Okay, that's how I understand this question. Next one. Similarly, dragging, right? Now this one is asking you which is the direction of frictional force. This is the direction of movement, right? To this side. So frictional force must be B. So B, there are 2 choices here. And then next one, which of them show the gravitational force? The gravitational force pulls things down, so this is gravitational force D. Okay, so answer is 4. Alright, let's go to the next question. So a coin that is tossed directly up into the air, and 4 children make the following statements. So which is true? Now here it says gravity is the highest when it reaches the point X. Now, well, gravity is a force that acts on objects that has mass, and there's nothing about highest or lowest. This is trying to confuse you in case you're confused about gravitational potential energy. So gravitational potential energy, an object that is at the highest would have more GPE. That's energy. Gravity is a force. So if you choose N, it means that you have confused force with energy. Now B, there is no force acting on the coin when it reaches the highest point. That's not true. If there's no force acting on the coin, then it will not be coming down, isn't it? If there's no gravity pulling it down. So Betty is also wrong. Gravity only acts on the coin when it has used up the upward force. There's no using up upward force and again, this is something like trying to confuse with energy. But the idea of using up doesn't make sense here. Force is not something like energy. You can, for example, use up, open and close inverted comma, the chemical potential energy in a battery. But the using idea is you convert it as another form. Forces, there's no converting of one force to another force. So this is trying to confuse you, so it's not Cindy. Gravity is acting on the coin throughout. So whether the coin is here, here, or here, as it travels up, there is gravity pulling it down. So Derek is correct. My answer is 4. Let's go to the next question. So 4 objects P, Q, R, and S were hung from the springs of the same type. The figure shows the length of the spring in each case. So there are actually 2 forces acting on the spring when there is a mass at the end. One force will be the elastic spring force that is pulling it upwards like this. And the other force will be the gravitational force that's pulling it down. Right? Now, so if the mass is greater, then there will be more gravitational force acting on the object, and therefore it will be pulled down more. Now, the size of the object may not be indicative of its mass. A big piece of styrofoam can have less mass than a small cube of metal or ceramic or something, right? So size doesn't mean that larger means it has more mass. We talk about how much is the spring extended. So this extension seems to be the greatest. Since the springs are of the same type, this one stretched the most. So Q must be the greatest mass. So this is the only one with Q. Now let's look at the next one now. Okay, next one. The picture shows two groups of children preparing to play a game of tug of war. So this means this group is pulling towards the left, this group is pulling towards the right. And after a while of pulling, the marker, which is this, is at the center, remains the same. Usually the idea is this: if the marker moves past, let's say, this line, it moves to this line, okay, it means that these people here in team A manage to pull team B towards the left. If the marker is here over this line, right past this line, it means that team B successfully pulled team A over to their side. So which is the correct explanation for the above? Since it did not move, it remained the same position, means did not move. Therefore, it means both teams are pulling with the same amount of force. Let's go to the next question. So Jessica wants to find out which brand of sticky tape, A, B, C, or D, sticks most strongly to paper. Now this is a slightly confusing way of presenting information, so you need to be careful. She did some tests using 4 brands of sticky tape, A, B, C, and D. She stuck an equal length of the different tapes onto the paper and measured the amount of force needed to pull each one off. So as I put a piece of paper here, for example, I put a piece of sticky tape over this, and then I attach some kind of mass. Okay, I'm just pretending it's not exactly the same. I'm trying to see if I can pull this off until the paper comes off from the tape. It detaches it, right? The force needed to pull each tape off. Now, of course, they are pulling it this side. The tape is here, paper is here. The setup is shown here. So we're trying to use the downward force on this to pull the sticky tape off. And they measure the force using the spring balance. The more the spring balance moves down, right, this is the marker, this here is at 0, then the more force is required to pull it. Now, and to be fair, right, the width of the tape got to be the same. If I use one tape of this width, another tape of this width, then of course you can say, oh, there's more sticky stuff on the other side that sticks onto the paper, so of course it's harder to remove it, you need more force. So therefore, when we're making comparison, for fair comparison, we must compare tape of the same width. So which one sticks the most strongly? You can see I marked the answer B, 2 is correct. Let's check why is 2 correct. 2 talks about B. Okay, so you compare 2, right? When the width is 2, which one do I compare to? I compare this reading, right? It means the width is at 2, giving about 145, 46 to 48 newtons of force to pull it off. If you look at C at 2 cm, 632, less force is required. So because C is not as sticky compared to B. Remember, the aim is to find out which tape sticks most strongly to paper. How about D? D is at 140, 41 is still less than B. How about A? 139, 134 for this, right? Still less than B. So why did I choose to look at 2? Because every single one of them has 2 cm as the width. I don't look at the 2.5 because there's nobody for me to compare with. Alright, and therefore, since it takes the most amount of force to remove tape B from the paper, therefore tape B is the stickiest. Let's go to question 8. Right, for students in my class, you would have done this, whereby I give you a board, there's a rubber band, you pull this object against this and pull it backwards. Then when you release your finger, which is holding onto the rubber band, then the elastic spring force in the stretched rubber band will push against the object and fling it forward in the opposite direction. Now, he places marble in front and he does all this. Now, which one shows the correct result of your experiment? When doing graph questions, it's always important to look at the axes and how it's described. So this is the length of the rubber band that is pulled. So in this case here, length means you're not measuring this, you're measuring how much is being pulled, measuring this length. When it's at 0, it means that nobody is pulling onto this. So when the distance of this rubber band that's pulled is at 0, it means that it is not being stretched. If it's not being stretched, then of course there's no elastic spring force in the stretched rubber band since you're not stretching it. Therefore, nothing is pushing against this, and distance traveled should be 0. That's how you know the answer here must be 1. This is the only one whereby when the length is at 0, this part is 0, the distance traveled by the marble is also at 0. If you look at this, they are saying that length of the rubber band is at 0, distance traveled is at a certain number. How is it possible you don't stretch it and yet the marble can move? Right, this is the same problem with this and this. Means at 0 cm of stretching the rubber band, you don't stretch the rubber band, yet the marble could move. So these 3 graphs are wrong because of this part here. Let's go to question 9. Now, so far, so good. Okay, Sam carried out an experiment to find out the elasticity of a spring. He hung different weights to the spring and measured the new length of the spring, and he plotted a graph. So which statement is a correct statement? Now I set the answer 2. Why? 2 is B and D. The extension of the spring is 4 cm and the mass is hung on it. Now let's recap some terms. If this is a spring with no mass, this will be the original or the initial length. And for the same spring, if you hang a mass on it and you stretches it, now there are now 2 new terms. This part here that is longer than the previous original length, this part is called the extension. And same here. And this new length that is longer than the original new length is called the extended length. Okay, so let's take a look at the terms here. Extension of the spring is 4 cm and the mass of 50 grams is hung. 50 grams put here, extension is 4. Okay, 50 grams, extension is 4, seems correct, roughly is there. Now, this is also how, if let's say you're confused between extension and extended length, you can also use a graph to help you. When you put 0 grams, there's of course 0 extension, 0 grams, right? Of course the spring is not extended. Only when you put some mass here, then there's gravitational force on the mass that it pulls the spring downwards. So when there's 0 load, there's 0 extension. The heavier the load, the longer the extension of the spring. Actually, I prefer the word the greater the load. Because heavier talks about weight. Let's talk about mass here. The greater the load, the longer the extension of the spring. So far it's true, right? More load, greater extension. More load, even greater extension. More load, greater extension. The more load you put, the more it extends. So B and D is definitely correct. Now C is wrong. It doesn't measure 10 cm. You put 200 grams, it actually extends by about 17, 18 cm. Now A is wrong. Original length is not 2 cm. I cannot tell from this graph what's the original length. It is not given because what's given is the extension. Next one. A parachute made of a plastic sheet box and some strings were thrown from the same height several times. So we couldn't do our parachute experiment yet. I hope we can get to do it soon. Okay. Now a box with some string was thrown here. It stayed afloat for a few seconds. Now when it's coming down, there will be something pushing against the canopy of the plastic sheet. This is called a canopy. Underneath here there's air. It's not nothing. And air is pushing against it. Here's your air resistance. And that is slowing the object down. And the pulling force, the gravity is pulling the whole box and the whole thing downwards. And because of this air resistance, it could slow down the movement. I couldn't stop it. If it can stop it, then it will be equal and be floating in the air, not moving at all. Since it's coming down gradually, it means that gravitational force is greater than the air resistance here, which is a kind of frictional force. So if you want it to stay longer in the air, you've got to slow down it even more, right? How can you slow down the pull even more? You can increase the air resistance by increasing the plastic sheet to a bigger plastic sheet. First, for those who are thinking a bit more deeper, the larger the plastic sheet, the more mass it has. Of course, the whole thing will be have more mass, so the whole thing will be heavier as well. So this cannot work indefinitely. You cannot use a plastic sheet that's this big. Alright, that can also create problems of its own. Another way is, of course, you can reduce the mass of the box. That will reduce the amount of gravitational force that's pulling on the whole parachute. Anyway, the answer is 4. Next one. Let's go to question 11. Now, a first mistake of the day. A group of children drop a tennis ball from a height of 100 cm onto different surfaces. Measure how high the ball bounced. These different surfaces. And they all drop from the same height of 100 cm. So 100 cm. They drop the ball on and they measure how high it bounces. Then they choose one of the 4 surfaces, didn't say which one, to carry out a second investigation. And the same ball was dropped from different heights, now it's different heights, onto this surface. And they recorded the height the ball bounced below. So, what can we use to compare? Which result? I chose the one in circle. I circled Y because the same height that it was dropped at 100 cm was recorded initially. The first experiment it dropped at 100 cm. The second one, in this particular case, the children also dropped the ball from 100 cm of height. Then I look at the value here. When it dropped at 100 cm, how high did it bounce to? 48 cm. There's no 48 here, but the number closest to 48, alright, seems to be, okay, it's not tarmac, seems to be clay, right? 48 is at 1 cm away from clay. 51 will be 3 cm away from this. So it looks like the clay surface, isn't it? It should be the clay surface. That's the closest bounce upwards when it's dropped on the clay surface. It's 47 cm, it's 48 cm. So which surface did they use? Clay surface. It cannot be the concrete surface like what you put here, because on the concrete surface it bounced to 61 cm. But in this case here, when dropped from the same height, it only bounced to 48 cm. Quite a huge difference. Right, the answer here is 1. Okay, now we go to open-ended question. If you are tired, you may pause the video and take a break. Okay, welcome back. So Ali hung some weights on a spring and measured the length of the extended spring. Again, extended spring. Let's recap. What does extended means? This is original length. This is extension. This whole thing is the extended length. So you're measuring the whole length. Okay. How can you confirm also? When there are 0 weights, the spring still has some length. Is it possible? Of course. It's just like this. You don't hang anything on the spring still has a certain length. What was the original length? Is when you don't put any mass, it's somewhere here, so it's roughly 5 cm. What was the extension? Remember, extension will be, this part is extension, when 5 weights were added. So 5 weights were added, it went to 14 cm. 14 cm is the extended length. So the extension minus 14 minus away the 5 cm. 14 minus 5, you get your extension, which is your 9 cm. 14 minus 5 is your 9 cm. Don't forget the units for this. What happened to the spring as shown by part AB on the graph? What happened on the spring? AB means here. Means after the 5th one, you keep adding a 6, 7, 8. The spring remains at this length. It can no longer extend. It's like this, no? You pull a bit. You pull some more until eventually it straightens the entire spring. Of course, it cannot extend anymore. A spring is a wire, it's not a rubber band. You cannot stretch it. Okay? Alright, so what must have happened? Now, it couldn't hit the floor because if you are putting a weight to the end, if you extend fully, it is the weight that's hitting the floor, not the spring hitting the floor. This answer has some sense to it, but it is just not possible. So what happened to the spring? You can pause a while and try answering this. So just describe what I showed you here. The spring has fully extended. That's the maximum. You cannot extend any further. So of course that becomes that's why the length of the spring no longer change. Okay, let's go to the next question now. So regarding the time taken for each sheet of paper to touch the ground, now this is the same piece of paper, but this is a squash piece with smaller surface area. This is an entire piece with a larger surface area. Because there's more air resistance, there's more surface. This is a paper from the side, right? There's more surface for the air to push against it as it comes down. With a squash piece of paper, the surface for air to push against it is much less. So what's the force that acts on the paper as they are dropped? Air resistance is the force that pushes it upwards. Gravity is the force that pulls it downwards. You can answer as gravity. There's no gravity force, but I accept this because at least it didn't say energy, okay? But the better term will be either you say gravity or gravitational force. Now try not to write this in test or exam because you may confuse your teachers. And if you are very picky, they may not accept it because they want to teach you the lesson that you need to use the correct term. Which paper will reach the ground first? Of course, the one with the less surface area, squash paper. Remember our CER. So the first thing your claim is worth 0 mark. So if you have a claim here, squash paper, 0 mark. Now you must explain it, okay, and a tip has been given to you, you must compare. So the comparison is to get your evidence, right? So you talk about squash paper at a smaller surface area. This is your evidence. Alright, and what's the reasoning? So that there will be lesser air resistance. So they have 1 mark here for the comparison and 1 mark here for the explanation. And the explanation needs to be a science concept. Whereas the evidence is something that's provided for you in the either picture or graph that you need to state your observation and your comparison. And that's how usually the observations are, you get marks for your evidence. Let's go to the next question now. This is just like the earlier question whereby you pull something against a rubber band that is stretchy, you let go, it moves forward. And if there are 4 similar tiles, right? They are coated with different substances. So you are changing the surface texture, making it either rougher or smoother. Now, which substance will be the best for applying the tiles to prevent slipping? To prevent slipping, it got to be something that's rough, increases frictional force between the bottom of the feet and the tile, surface of the tile. So again, your claim, remember your C, E, and R to get your full 2 marks. Claim has no marks, 0 marks. Evidence, 1 mark. Your reasoning, 1 mark. So claim here, why? Okay, whether it's right. If it's right, you get 0 mark for it, but we will be on to look for your evidence and the reasoning. So the evidence now comes from this part. You see 4 different numbers here. Why did you choose 15? Because when you compare against the other 3 numbers, it is the least. So the first one is from your evidence. The block moved the least. See, move the least compared to the other 3. There's 1 mark for your evidence. Okay, now you need 1 more mark, which is your reasoning. Why did it move the least? And therefore, how do you, based on that, choose this material as the one you will place on bathroom tiles to prevent slipping? Well, it has the most frictional force compared to others, so it's okay, prevents slipping. This is good. However, frictional force doesn't appear on its own, right? Frictional force opposes direction of motion, and frictional force is a contact force, so you have to mention the 2 surfaces. No surfaces were mentioned here. By itself, this piece of paper has no frictional force. Only when I try to slide something across it, then there's a frictional force in this direction. If it's not moving on a flat surface that's not an inclined plane, there's no frictional force acting on my pen at all. So how will you answer this to get your reasoning mark? And this is how I suggest you can answer the second part to get your reasoning mark, your R here. How? We talk about how this surface is the roughest, and how do you know? Because there's the greatest frictional force when these 2 surfaces, surface of the glass is a glass block that was moving across it. So the bottom of the glass here, this is the surface of the glass, and the material Y. Material Y was applied onto the tile, right? Material Y was applied onto the tile. So, and that is the other surface that it is coming in contact with. And this is how you get a second mark for your reasoning. Let's go to the next question. Okay. Now, Andy built a toy hovercraft as shown below. The hovercraft was able to move on a carpeted floor. So he used rubber as the base and he strapped on an inflated balloon to it. Now, before he let go of his toy hovercraft on the carpeted floor, he had to release the clip on the balloon. So for questions like this, you need to read the words which are meant to help you to understand the picture. There are so many moving parts, right? Rubber, elastic band, clip, clip. You must remove the clip. And if this inflated means that air inside and a balloon is made of rubber and the rubber is stretched in an inflated balloon. When the clip is removed, the air inside will start to gush outwards. As the air inside gush outwards, what's outside? What's outside? This water? Air. Air is all over the place, right? All surrounding this. So there's a wall of air right here. So the air that's inside the balloon will gush out and push against the air that's outside. As you push against it, you will move this whole thing in this direction. So in relation to force, so you can use energy to answer this. Why the toy hovercraft was able to move? So I give you two clues here. Firstly, what was pushing the hovercraft? Second clue, wasn't there frictional force? First, you can push all you want, but if the frictional force is greater than the force that you're pushing it, it still wouldn't move. So in order to move, there has to be two components to this idea that allows the object to move. Think about how you will answer this and try it now. You may pause the video. So I'll suggest this way of answering the first one. What was pushing the hovercraft? The air in the inflated balloon gushed out and pushed against the surrounding air. So that pushed the hovercraft in the opposite direction. That's the first thing. And in order for it to move, this pushing force has to be greater than the frictional force. It has to overcome the frictional force between the rubber and the floor in order for it to move. Now, in the same line of reasoning and understanding, if there's a question as to, after a while, the hovercraft stopped moving, explain in terms of forces why it stopped moving, you can use the same conceptual understanding to explain it. For example, you can say this. When the pushing force lessened and is equal to the frictional force, the hovercraft stopped moving. Because once it is equal to the frictional force, it can no longer be greater than it. It can no longer overcome frictional force. Then it will stop moving. Without changing the toy hovercraft, what could Andy do to make the hovercraft move at a faster speed? This question is only about suggestion. What can he do? There's no explanation needed, so there's no need to give one. Just need to say, for example, you can inflate the balloon more, okay. By inflating the balloon more, you are now increasing the pushing force when the clip is removed, or you can apply a layer of lubricant to the surface, so to reduce the frictional force between the rubber and the carpeted floor. Or you can change this to a different floor. You see, the condition here is do not change the toy hovercraft. Blowing more air into it is not, you are not changing the hovercraft. But it didn't say you cannot change the location of the experiment. You can change it to a floor that is a smoother surface compared to a carpeted floor. Now, hovercraft is a real thing. You can search on YouTube, right, type of hovercraft. Below is a cross-section of a real hovercraft. Now, of course, you can't have balloons on the real hovercraft, right, to keep blowing air out. Because the air inside there will run out. So instead of air in the balloon, they have fans that actually blows the air in the opposite direction. So if I draw the hovercraft sideways, and the fan is here, blowing air in this direction, then of course the hovercraft will move in the opposite direction. And below there's also the fan pushing some air downwards. Why? So you create an air cushion so that the hovercraft is lifted above the surface, doesn't touch the surface but instead touches the air. Is there still frictional force? Yes, between the air and the ground, but there is so much less frictional force compared to if the hovercraft were to be touching the ground. So how does the air cushion allow the vehicle to move easily on water? I just talked about frictional force, right? So it will reduce frictional force, yes. How does it reduce frictional force? That's the question here. How would you answer the part about how it reduces frictional force? I think this is a pretty good answer, but I just thought let's extend our understanding a little bit more. So how does the air cushion help to reduce frictional force? Well, by simply not letting the hovercraft touch the water. So imagine if your shoe is like a hovercraft, if your sport shoe can generate an air cushion between the rubber sole and the ground, so your rubber sole is not touching the ground, okay, if it is your special shoe that you go to school with, and this is the ground. If there's an air cushion that can be generated so that you are floating on the air, you're touching the air, not touching the ground, of course there will be less frictional force, right, between the sole of your shoe and the ground because they're not even touching each other. So by not letting the hovercraft touch water, the air cushion reduces the frictional force between these two surfaces. That's how the air cushion helps. Let's go to the next question. Oh yeah, I mentioned video. So I will search for a video that explains this, that shows a hovercraft at work. And if I can find it, I'll put it in the description box below the video. So check out the description box. If you see a video link there that says hovercraft, that's the one. Okay? Alright, let's go to this question. It's on magnetic force. Now, 3-bar magnets were hung above a tray of iron pins. Let's observe 5 pins here attracted to C, 5 pins to B, 5 pins to A. Hey, it seems at first they are of equal strength, but no, that's not true. If A can attract 5 iron pins, when it is further away from, when it is furthest away from the tray of pins, and remember, magnetic force is a force that exerts at the distance, and it weakens as the distance increases. It becomes stronger the closer the magnet is to the magnetic objects. So this is the strongest. That's a claim. Alright, 0 marks for claim. Explanation. Before explanation, remember our C, E, and R. So a claim has been given. A is a claim. Alright, now the evidence is to compare against this. It can attract the same number of pins at the furthest distance. This is the evidence. Alright, and the reasoning, okay, is already given because this reasoning is given here. Magnet is the strongest. Therefore, you can write, therefore A is the strongest magnet. But that will be repeating the stem here, which you can write, it's okay, but that's not necessary here. Okay? How can it increase? How can you now make a permanent magnet lose magnetism? You can hit it over heating a hot plate or throw it inside fire, or you can hit it by using a hammer or keep throwing it on the ground. Of course, try not to damage things, please. What's the force that causes a pin to be attracted to all the magnets? That is magnetic force. We're coming to the end of this video, so hang in there. Now, when you talk about frictional force, you can talk about things on an inclined plane like this. There's a solid plastic cube placed on the top, and the time taken for it to reach the bottom of the ramp was recorded. Then they changed the smoothness of this surface by putting different amount of talcum powder. What powder is this? It's actually just baby powder that they put on the body after they bathe. Alright, they put powder on the ramp, and the result were recorded in the table below. So when there was no 0 teaspoon of talcum powder, it takes 9 seconds to travel from the top to the bottom of the ramp. But when you put up to 3, it takes just 3 seconds. Just shoot, slide across 3 times as fast as this. It took less time. The more powder you put, the less time it takes, which means the faster it travels. So what was the aim of the experiment? Now it's very, very common for students to just relate these headings here and write something like this. To find out if the time taken by the cube is affected by the number of teaspoons of talcum powder spread on the surface. But that's not a scientific reason. Why would this person want to find out whether the time taken by the cube is affected by the number of teaspoons of talcum powder? That's nothing to do with science. So why would you want to measure this? What does this time measured suggest to this person? Remember, force is something you can see the effects, but you cannot see the force itself. So you're going to observe something to give them some clues as to how can I reduce frictional force. So the idea is this. If let's say this person wants to find out whether the plastic cube is a plastic cube, whether a plastic cube will move faster if the frictional force between the cube, between it and the surface is reduced. So you're trying to find out this science part. If I reduce the frictional force between the two surfaces, will the plastic cube move faster? To answer either a yes or a no, we need something that we can measure, right? we can measure the speed, we can measure the time taken. And the time taken, whether more or less, will tell us whether the frictional force really will affect the speed of the plastic cube as it slides down. If it slides down faster, it means that there's less frictional force here between the two surfaces. If you put down more teaspoon of the powder and it actually slows it down, it took maybe 20 seconds, that means then, of course, it will increase friction. So basically the idea of this, for this answering this question, I think most of you will get it wrong, right? If you are trying this question, which is you will tend to just use this. But these are just variables here. This is a variable that you change, number of teaspoon of powder. This is a variable that you measure, the time taken. But this doesn't tell the science behind why this person did the experiment. The science here is linked to frictional force. Reducing frictional force will reduce the will increase the smoothness of the surface, therefore will reduce the time taken for the cube to travel down. How do we know? Yeah, measure the time taken. Okay? State the relationship between the amount. This is, of course, simple. It just states the relationship between the amount of talcum powder spread on the surface and the time taken. Now, don't change the question, please. So, the time taken is not speed. Right? Speed is equals to distance over time taken. These are three different values. If you talk about time taken, then focus on time taken. Don't change it to speed. Faster is speed, it's not time. Okay? So I'm sure the question, you know how to do the correction for these things. Why the addition of the powder affects the time taken by the cube to reach the bottom of the ramp? Why the addition of the powder? Remember we talked about the why early on as with this part? Because it decreases the frictional force, the friction between the cube and the ramp. Very good. Talk about the two surfaces. Here we talk about springs. Different length of springs when add P to it. Now these are 4 different springs. So you will understand that if the springs are different, the elastic spring force will be different when you stretch them differently. And now this bar graph has 2 parts, a shaded part and an unshaded part. The shaded part tells you that is the what is the change to the length of the spring when you add the P, and this tells you the original length. So for A, B, and D, the original length is the same, whereas for C, it was longer. In other words, A spring is like this, B is like this, D is like this, whereas C is a longer spring at first, even before you add anything to it. Okay, what force do springs A and D exert? First, springs exert elastic spring force. Based on the graph, what's the extension? A recap again. Original, extended, extension. So this is the extension part. Now, why is 20 wrong? When P is added to A stretches to 20. That means it went to 20. Original length is 10, see, 10. So the extension is actually this part, 20 minus 10 is 10. This should be 10. Which of the spring is compressed when P is added to it? Let's see. So compressed means that the spring gotten shorter. After adding P, this is the original length, and this one becomes shorter. So it must have been compressed by something on top. Okay, so that's C. Give a reason, the length of this spring decreased. That's the correct answer. So when weight P is removed and another weight is added to spring D, the spring stretches less than before. Right, D here, it stretches less. That means that Q has less mass than P. Okay, less mass. Now, mass never use heavier and lighter to talk about mass. The words heavier, the words lighter talks about weight, and weight is a force that's linked to gravity. If you're in outer space and you're floating in orbit, alright, Mr. Long here has more mass than you, I'm quite sure. Let's say my mass is 70 kilograms. Let's say your mass is 50 kilograms. But if we both stand on a weighing scale, our weight will still show as 0 when we are orbiting around the Earth. Weightless. So, but our mass can still be different, but weight will be the same as 0. So don't use lighter because it gives a wrong concept here. Use the word less. Weight P has less mass than P. Mass, okay? Less mass than P. Now, last one. This is slightly trickier, last question. In an experiment, Harif placed 2 cylinders, A and B, on a marble table as shown. Cylinder A has rubber grooves on it, B has a smooth surface. The 2 cylinders have the same mass and same volume. When the cylinders will roll across the surface, the marble table at the same time with the same force. Which cylinder will roll faster? And give a reason to talk about it. Now let me think about this. I think, the answer is correct. Is A, it has less surface in contact. It's true. And why did I change my answer? I'll explain in a while. Because this is a marble table, it is a solid table. This is not a soccer field, which is a different story altogether. Now, if that's the case, there's less area of contact. Yeah, I think the frictional force here could be less. Now, these 2 objects have the same mass and same volume. Now, I'm hesitating here because of the experiment that you could have done before. Alright, let's say I have 2 blocks, both at 10 kg, 10 kg. And this is a surface in contact with the tabletop. Now, comparing the 2 objects of the same mass, B obviously have more surface in contact with the tabletop compared to A, right? Bigger surface in contact. Then, which of these, if you try to pull with a spring balance across the table, will actually shows you more force needed? Usually the answer is the same. The frictional force is not affected by the surface, the amount of surface in contact. It's not. So in this case here, when the cylinders have the same mass, same volume, but different surfaces in contact, I'm wondering, is it a trick question? Because I would think that if that is the case, based on the understanding from this experiment, they will actually roll at the same speed because the surface area in contact does not affect the frictional force. That's why I thought, let's test it out, okay? If you are a student in my class, we will set up an experiment where we will try this out. Let me think of how we will do this. At the moment, I think I'm comfortable accepting this answer because it goes against whatever you say here. So I'm not going to put a tick here and change my mind again. So this one, let's put in question because I think that actually the answer should be the same because the surface area in contact does not affect the frictional force. Same. Surface area in contact, amount of surface area in contact does not affect frictional force. So that is how I will answer this. Which is kind of odd because the way the question is designed only provide 2 options for the students. Either A or B. There's no same. Okay. Now, the different story right now is this. In track and field events, track spikes are used rather than flat sole support. Why? If you talk about surface in contact, if there's less surface in contact here and that doesn't affect frictional force, why would they use spike shoes? Like in soccer, for example, they play on the soccer field. Actually, when they have spike shoes, it will actually increase the surface area, not decrease. Why? For example, if this is the surface, a rubber surface or grass surface, doesn't matter, they are soft surfaces. If I wear a shoe on it, like this, a flat sole shoe, this will be the surface in contact. But if I were to wear spike shoes, try to draw the same size here. Like there are spike shoes. Now I'm going to zoom this in, okay? Bigger right now, zoom this in. Now I notice that the surface is no longer just this part, in contact, but also this part in contact. In contact with what? With the ground. And when it's a soft ground like grass, like soil or track, it will be this rubberized surface. Previously, the surface in contact is this part and this part here. Now it has increased to this. See this? Having spike shields on surfaces that are softer allows the spike to go in, actually increases the surface area in contact and make it somewhat increase the frictional force. Okay, so here should be increasing, it will provide better grip. So why do they have this? The spikes improve or increase the grip between the shoe and the ground. Okay, the spikes improve or increase the grip between the shoe and the ground. Alright, that's the end of this lesson. I hope you enjoyed this. Take care. I'll see you in the next one. Goodbye.